Welcome to today's experiment. The name of the experiment is Melde, and the aim of the experiment is to study the frequency of the electrically driven tuning fork in transverse and longitudinal position. So the apparatus required for this experiment are the tuning fork, thread, weight box, pulley, pan and AC power supply. So now, before starting with the experiment, just theory behind this experiment is electrically tuning fork and resonance are involved in this experiment. So as we are using the AC power supply, which consists of 50 Hz frequency, that 50 Hz frequency is given to this tuning fork, and when the tuning fork is set into vibration with the help of this AC power supply, and when the natural frequency of this tuning fork is matching with that of the 50 Hz of the AC power supply, then the tuning fork is set into vibration and we hear a booming sound. So finally we can say that as the tuning fork is set into vibration, those vibrations are catched through the loops attached to the thread. So now we can set this tuning fork in two positions. One is the transverse position and another one is the longitudinal position. So first we are going to study the tuning fork set in the transverse position. So the basic definition of the transverse position is the vibration of the tuning fork is said to be perpendicular to the loops. So here when the tuning fork is set into vibration, now the main point to remember in this experiment is we should not see the position of the tuning fork. We should see the vibrations of the tuning fork. So if the vibrations of the tuning fork in this setup is, we call this setup as a transverse position. Now the tuning fork will be vibrated in this position and the number of loops can be seen in this position. So the tuning fork is set in this way and the loops are set in this way, so that we can say that both are perpendicular to each other and we can say that the transverse position. So now coming to the experimental procedure, you have to switch on the power, add some minimum weight. Say for example, we can say very little weight for the sample. We can say now I am going to add this much of weight, which is of 1 gram to the pan. So when I add this weight to the pan, now when I switch on this power supply, I should make this power supply a contact through this motor which is set in between the tuning fork. Now I just made a contact so that the tuning fork will set into vibrations. A spark will be seen. See, the tuning fork is set into vibrations and very little, just a point contact is enough so that we can see the loops. Now you can see the loops here, 1, 2, 3, 4. So I'll say again 1, 2, 3, 4. So the main precaution in this experiment is, see here, the tuning fork is vibrating in this way and the number of loops we can observe in this way. So the tuning fork is set into vibration. The main precaution while doing this experiment is whatever the length of the thread you should maintain, always we should count only the full number of loops. We should never count a half loop which lies halfway between the pulley and the thread. So always we need to count the number of full loops. That is the main precaution in this experiment. Now when you see this, the formula for finding out the frequency of the tuning fork in the transverse mode is n is equal to 1 by 2L into root T by M. So the tuning fork is set exactly that way. When you see the parameters here, M is the linear density. So the linear density is total mass of the thread by total length of the thread. So this is standard way which we can say by using the balance we can find out the mass of the thread, and total length of the thread has to be always calculated between this end to exactly the midway of the pulley. So from this point to this point, take a 100-meter scale and measure like this. So this is 100 meters, make a point of note of this and again between the center of the pulley. So it is approximately 141 centimeters. So total length of the thread. So now when you see this total mass of the thread, it's a constant given by the suppliers. L is the length of the each loop, T is the tension in the tension created in the thread. So T is equal to, how can we calculate is T is equal to M plus P into G, where M is equal to the mass added to the pan in the grams and P is the mass of the pan, which is already noted at the bottom of the pan. See here, mass of the pan will be noted by the suppliers. We can see here the mass of the pan, and length of the thread, mass of the thread will be given by the suppliers. Next, G is the acceleration due to gravity. So everything is taken in the CGS system, so we can calculate the value as 980 dynes per centimeter square. Now the first point is, as I said, like if I add 5 grams to the pan, now what is the tension that is created and how many number of loops are created, then what is the length of the each loop, then root T and root T by L. Because in the formula, see here, the frequency of the tuning fork is N is equal to 1 by 2L into root T by M. So when I alter this, you can say this 1 by 2, I am taking this denominator outside, 1 by root M into root T by L. So our calculations are mainly dependent to calculate the value of root T by L, which is a part of the formula. So to calculate the root T by L, I am using all these parameters. So first one is, I added a weight which is of 5 grams in the pan. Next, I have electrically driven the tuning fork so that I got 10 number of loops. So now when I see this, tension created is, what is the tension that I have created is T is equal to M plus P into G. So M plus P into G, I can say in this formula, total length of the thread is 160 centimeters, which I have calculated from the 100 meter scale. Total mass of the thread is 0.4 grams, means total mass. Total mass here is from this point to this point, where I have attached the pan. When I am counting the pulls, I should count only up to the pulley, but when I am counting the total length and total mass, I should check the total thread, which whatever that is given for the experimental procedure. So this we can take as standard given by the supplier. So total mass of the thread is 0.4 grams. Now first thing is to find out the linear density. Linear density is mass per unit length. So 0.4 by total length of the thread is 160, which is calculated to be 2.5 into 10 power minus 3 grams per centimeter. Now mass of the pan, as I said, which is given on the back of the pan, so which is equal to 7.87 grams. So that will be given by the supplier itself. So first one is, when I calculated this mass per unit length, mass applied is 5 grams. So I have added 5 grams to the pan. I have added 5 grams to the pan. Now I have set the tuning fork. I need to count the loops, 1, 2, 3, 4, like that. So for this experimental procedure which we have done, when I add 5 grams, I got 10 number of loops, and I have calculated the tension T is equal to M plus P into G. M is the mass added, which is equal to 5 grams. Next, P is the mass of the pan, which is equal to 7.87 grams into G is 980 dynes per centimeter squared. So I get the value of 12612.6, and number of loops that I have formed when I add 5 grams is 10. So length of the thread is the distance between this knot to the pulley, exactly pulley, so it was equal to 141 centimeters. Now I need to find out the length of each loop. This is the length for the total number of loops that I got, but I have to calculate only for one loop. So 141 by 2 by 10, which is equal to 14.1. So this is equal to the length of the each loop, which I got it as small l. Now what is root T means? The tension that we have calculated. So root of 12612 is equal to 112.30, and root T by L means root T is 112.30 and L is length of each loop, which was equal to 14.1, so 7.964. So now in this way, there are many ways to calculate the frequency of the tuning fork. One way is to keep the length as constant and always count for even number of loops. But the second way is by varying the weights that are added to the pan and counting the number of loops, keeping the length of the thread as constant. So in this method, we have find out out the length of the thread is constant for all the readings, and we have varied the weight that is added to the pan. So we have done the experiment for 5, 10, 15, 20, 25, and we have calculated the number of loops. It will be vary because we are keeping the length of the thread as constant, and every time we have done the calculations, and finally for certain type of like 5 readings the average was equal to root T by L in the transverse position. Now substitute this root T by L in the frequency formula, which was equal to n is equal to 1 by T into 1 by root m into root T by L. So 1 by T by 1 by root Tm means the linear density mass of the thread, 2.5 into 10 power minus 3 in root T by L is from the tabulation, so which was equal to 8.4146. So after doing the calculations we can say that n is equal to 81.46 hertz. So you know that hertz is the unit of the transverse position. So the main part is many of the people will be confused like the position of the tuning fork and the vibration. So the glance we can say that it is in the longitudinal, but it is wrong. We need to see the position like how it is vibrating. So the tuning fork is vibrating in this position and the loops are seen in this position. That's why this particular setup is now called as transverse position. Now we go for the second part of the experiment, that is to find out the frequency of the tuning fork in longitudinal position. So how can we define the longitudinal position is the vibration of the tuning fork should be parallel to the number of the loops. So now the tuning fork is set into vibration again with the same procedure, and we will go on changing the weights that are added to the pan. So first I will start with the adding the 5 grams to the pan. So this is 5 grams. Now when I start tuning the frequency, the same spark will be coming out from the motor. See here, when I see the spark, they should not touch with each other. When I see the spark, the number of loops we can see 1, 2, 3, 4. So every time we need to count only the full number of loops. Suppose if you are getting any half loop, then we should vary the length of the thread, or we can vary the weight that is added to the pan. So this position where the vibration of the tuning fork and the loops, that is the disturbance of the tuning fork passed over as the loops in the thread, both are in parallel. So this position is called as longitudinal position. And the formula to find out the frequency of this tuning fork is, I will switch off because of the sound. Now for the calculation purpose, the frequency is n is equal to 1 by L into root T by M. So earlier it was 1 by 2L into root T by M. Here in the longitudinal case, if I rearrange the terms, I can say that 1 by root M into root T by L. Again the same thing, M is the linear density of the thread, root T is the tension, which is M plus P into G, and L is the length of the each loop. So load that is added is 5 grams. The number of loops that we have counted is 5, and T is equal to M plus P into G can be taken as T is equal to M. 5 plus P is the mass of the pan, which we have taken it as see the mass of the pan is taken as 7.87 grams. So now we have to substitute it in this formula 7.87 M plus P. For your easiness, I can show it as T is equal to M plus P into G for one calculation. So T is equal to M plus P into G, where M, the mass that we are added is 5 grams, plus P, the mass of the pan is 7.87 into 980. So 12.87 into 980, which is equal to the value that you get 12612.6 12.6. So that we have calculated here. T's tension is 12,612.6. So number of loops is 5 and the length of the thread has to be calculated from this end to the pulley. So as we are using the 100 meter scale, the entire 100 meters is count. So take this point as a reference, and from here if you take till the loop, it is around equal to 141 centimeters. So 141 centimeters. Now this is the entire length from one end to the pulley end. Now we have to find out the length of each loop. So length of each loop is 141 by 5, which is equal to 28.2. So root to T is root of tension. Root of 12612 is equal to 112.30, and root T by L is this by now length of each loop, which is equal to 28.2. So root T by L is 112.30. We can find it as root T by L is equal to 112.30 by the length of each loop is 28.2, which is equal to 3.982. Now how we are going to do for the second reading is change the weight, increase the weight. Now I am adding 10 grams. So first I have started with 5. Now I am going to add with the 10 grams. Now we should see how the variation of the loops will take place. So the number of loops, as we are increasing the weight, the number of loops will reduce. So the number of loops is, see here, earlier it was 5, now it is only 4. 1, 2, 3, 4. Like this, if you go on adding the weights, either the length will be decreasing or the number of loops will decrease. See the case 1, 2, 3, 4 only we are getting. So I have added the weight of 10 grams. Now the number of loops is 4. As usually when I change the variation, m plus p instead of m. Now I vary it with 10. So 10 plus 7.87 into 980, I am going to get 17512, and I am not vary the length because I didn't get the half loops. So 141. Now length of each loop is 35.25. Root T is root of 17512, 132.3, and root T by L is 132.33 into by 35.25. So 3.754. Like that I will vary. Now I am going to vary 20 grams, next 30 grams. So like that I can vary the weights. So as I have interested with the 4 readings, I started with the 5, 10, 15, 20, and every time I have counted with the loops, keeping the length of the thread as constant, and the number of loops I counted with. So finally when I take the average of root T by L, I got it as 4.1305. So in the longitudinal position, exactly it was half that of the transverse. So in the transverse it was equal to 8.146. Now it is equal to 4.1805. But theoretically we should say that since the number of the loops are half when compared to the transverse and longitudinal, so that's why we have included a root 2 by L in one formula and root by L in longitudinal position. So finally, as we are supplying only the 50 hertz of frequency to the power supply, either in the transverse or longitudinal position, we need to get the same frequency of the tuning fork. So here the resonance is heard in terms of booming sound, whereas in the case of that's why we call it as mechanical resonance in this case. Suppose if you are going for the electrical resonance by using the electronic circuits, like in the LCR experiment that we have already done, we can see either the dip in the frequency curve or peak in the frequency curve. So peak we observe in the series and dip we observe in the parallel. So here in the case of mechanically tuning for frequencies, we hear a booming sound. That why when you on the experiment we hear a booming sound. So finally, after doing the calculations, root T by L formula, so total length of the thread is 160 centimeters. Now 1 by this was equal to the tuning fork frequency. Now 1 by root m into root T by L in the longitudinal position. So 1 by root m is 0.05, as we have calculated the mass, linear density, into 4.1305, which is equal to root T by L in the longitudinal position, 4.1305. So 20 into 4.1305, which is equal to 82.61. So the result is the frequency of the tuning fork in transverse is 81, frequency of the tuning fork in longitudinal is 82.61. So approximately equal. So either in the final note is either in the transverse or longitudinal position, as we are using the same tuning fork, the frequency should be same. So this is what the Melde's experiment is. Here we are electrically vibrating the tuning fork and finding out it in the electrical resonance by hearing the booming sound, and the disturbance is observed in the form of loops. Thank you.